Ah, there you are, Explorer. Welcome to Day 18 of our fantastic interstellar adventure. I hope you're well rested and ready to embark on today's journey. Great work on the last mission, Sherlock. You've got the brains, but now we're gonna need the brawn. Your keypad worked fine for real-time input into the Hero, but we'll need precise thrust control for our ascent rate to the surface without risking any, let's say, unplanned rapid disassembly. Or we could run straight into Rachel, and same thing, game over. Fortunately, the Hero Kit contains just the sensor we need for subtle or forceful control, a rotary encoder. All right, let's dive into today's hardware discussion. Our star of the day is the rotary encoder. But what exactly is it? In simple terms, a rotary encoder sends direction of rotation signals and the amount of turn. It can also send an on or off signal with a push. Pick it up and play with it. Every click you feel as you turn the encoder is counted, and the direction you're turning it is noted. These two pieces of information are sent to our board as a sequence of high and low signals. The rotary encoder is particularly useful for scrolling through menus, adjusting variables on the fly, and in our case, delicately controlling our ascent rate. Moving on. It's time for some nerdy distinctions. There are two types of encoders, absolute and relative. An absolute encoder has a unique value for every specific angular position of the knob. There's a maximum clockwise position and a maximum counterclockwise position. You know precisely where you are at all times. A relative encoder, on the other hand, like the one we're using today, can turn endlessly. It doesn't have an end, so to speak. It tells you how far and in which direction the knob has been turned from its starting position, but it doesn't give you a specific location. Our relative encoder has 20 distinct clicks for a complete 360-degree rotation. That means each click corresponds to an 18-degree rotation. That's our encoder's angular resolution. Now that we have a good understanding of our new component, let's talk about how we're going to hook it up to our control panel. We connect the 5V to the plus symbol, or VCC terminal, and ground to the GND terminal. CLK, or A, and DT, or B, are the clever bits. They help us figure out which way the knob is being turned. There's also an SW terminal. That's for the push switch built into the encoder. Push down on the knob, and it acts like a button. Neat, huh? But we won't be using that feature in our project today. I think it's time we move on to the code. Wouldn't you agree? Right, let's get a bit technical now. This rotating encoder gadget is all about timing. We want to know two things. 1, the direction of rotation, and 2, the rate of rotation. The direction of the rotation is rather straightforward. When the knob starts turning, one of our two signals, CLK or A and DT or B, will get excited and go high before the other. Which one goes first tells us the direction of rotation. Essentially, if our CLK signal gets all giddy and turns high before our DT signal, we know the rotary encoder is spinning clockwise, like the hands on a traditional clock. If, on the other hand, our DT signal jumps the gun and goes high before CLK, we know the rotary encoder is spinning counterclockwise. Isn't that just a slice of fried gold? The rate of rotation is a bit more complex. I think we'll save that juicy bit for later. For now, let's make sure we get that direction detection working perfectly. Right, so we know that the order in which our signals go high determines the direction of rotation. But how do we accurately and efficiently detect that? Enter our secret weapon, the interrupt. An interrupt is a rather brilliant feature in microcontrollers that says, "Hey, listen! Something important just happened. Stop what you're doing and pay attention to this right now." This allows us to interrupt the normal flow of our code to react to a specific event. In our case, when either CLK or DT goes from high to low or from low to high. Or, in simple words, when either CLK or DT change their state. Instead of continually asking, "Are we there yet?" to CLK or DT in a loop, which is very tiring, mind you, we set an interrupt on CLK and DT and then go about our business. As soon as one of them changes state, the interrupt fires and our code can react immediately to handle the event. Once the interrupt executes, the code will resume exactly where it left for the interrupt. It's like setting an alarm to wake you up at 7 a.m. instead of waking up every few minutes to check the time. It's efficient, isn't it? That's the magic of interrupts for you, Explorer. Right. Today, we've got 2 primary tasks to tackle in code. Task 1. We need to read the direction our rotary encoder is spinning, which we'll manage by using a counter of sorts. Consider it our trusty breadcrumb trail to keep track of where we've been. Task 2. We have to ensure our spacecraft doesn't leap like a giddy frog from altitude 0 to 100. Stick with caution. Sudden rises could rip holes in the hull from rocks. Rise too slow, and there might not be enough force to get unstuck from ocean mud. Constant rises could run you into Rachel, the giant whale-like creature hovering around the ship. We need to maintain a steady, controlled ascent, and that means putting safeguards in our code. These are specific stopping points at precise altitudes. We'll use our 7-segment display as our handy altitude meter and adjust our altitude with the rotary encoder. We're not competing in a high-speed race, so there's no rush. Remember the fable of the celestial tortoise and the comet hare? That's right, we're taking a page from the tortoise's book. Slow and steady wins the race. Adjust the altitude, check the display, and ensure the steady ascent of our craft. 1 step at a time, my dear intrepid explorer. Woo! If I had a human voice like you, I think I'd have lost it by now. I think it's time we turn to some instructional material that I've gathered, cached on the computer. I've also added it to your, well, you know the drill.
Hello and welcome to day 18. Before we start, did you get the numbers from yesterday? Did you write them down? Do you have them? Because if you don't, today will not work for you. So make sure that you have the codes from yesterday. And if they aren't working, please be sure to check that, make sure that you shifted with numbers included. But if you shift with just the alphabet and not characters 0 through 9, it will not work. So make sure, once you have those numbers, you'll have this down here, which is the keys that are needed to unlock your control system. If you don't have all 3 of those keys, you will need to replace this with the first, this with the second, and this with the third key. So make sure you do that. Otherwise, your code will not work. It will not compile. In order to reduce any risk of unauthorized use, that is why there is such a high security on the controls. New concepts that we'll be talking about today when it comes to coding are interrupts, which allows the currently executing code to be, well, interrupted, to handle some event and then return to the executing code as though nothing had happened. You can think of it as like in the middle of me talking, someone tap, "What's up?" Okay. And then coming back to the speech like nothing happened. That's my way of interpreting it, I guess, internally, although it's maybe a strange example. Down here we have another function which is going to allow us to use those interrupts, which just simply says attach interrupt. We're essentially going to attach an interrupt on an event, or when something happens, it's going to trigger the interrupt to occur. Then we have digital pin to interrupt, which converts a pin number to an internal Hero interrupt pin. Please note, the Hero board only supports interrupts on pins 2 and 3. Any other pin will not work for interrupts. New parts that were introduced in this lesson include the rotary encoder, which allows the sketch to respond to rotational input, clockwise or counterclockwise, and can also provide a button input when pressed down. And since I'm using the Arduino IDE for this example, I don't need that. I'm going to remove it. But if you're not using the Arduino IDE, let's say you're on some other simulator out there, maybe Walkwii or using Visual Studio, you will need it. Next, we're going to include the 7-segment display library that we should hopefully already have installed if you went through the last couple days. And then there's a new library that you need to have installed. Again, inventor.io/libraries. Go download the zip file, go to Sketch, include library, add zip library, and include the basic encoder library. assuming you have all your keys put in here correctly, which I hope you do, we can continue on forward. Now, I don't want you to get confused with the 7-segment display pins and the rotary encoder pins. They both have clock pins, and they both have, this is a digital input output, and this has a DT pin. They look very similar at a glance. This is going to be defining the pins for our rotary encoder, and this is going to be defining the pins for our 7-segment display. Try not to get them confused. They do look very similar though. The rotary encoder is used for the depth controller, and then the 7-segment display will be our depth gauge displaying what depth we are at. Now here we have the basic encoder object, just like the 4x4 keypad library where we needed to create an object, just like the 7-segment display library, like here where we had to create an object. We need to create an object for our library so that we can call the code. We're going to call this one depth control for our rotary encoder, because it's quite literally going to be our depth controller for rising us back to the surface. What it needs to function is a object. It needs to know what pins it's going to be talking to. In this case, again, 2 and 3, which we defined right here. Down below here, we're also just going to set a global variable up above, which says blink count. Now, this is going to be used later on in the code. For now, it doesn't make a lot of sense. It's just a variable 3 that's not going to be changing at any time, which is just a blink depth gauge this many times for attention. We chose 3 because we thought that would be a good number, but if you ever want to change it, all you got to do is change one variable up above instead of it in 50 places down below. As you probably remember, done is one that's here for the 7-segment display. That's all stuff we talked about before. Then we have the constant byte nope, which again, very, very similar idea to what's going on here. N-O-P-E. Now, our lander is currently at this depth underwater. So that's what we want our initial depth gauge display to be showing. 60, negative to be exact. Negative 60. Where 0 would be the surface of the water, which is defined, well, here. We want to alert the user when we rise above this depth. Remember, we don't want to go too quickly. The first depth we want to be careful about stopping at is negative 40, and this one is going to be negative 20. Now, setup today is a little bit more complicated than what you might have been used to for setups. Yes, we're doing a little bit more today, believe it or not, than just setting our serial monitor and some pinouts. We have a little bit more because we are introducing the concept of interrupts. We're going to start the serial monitor, and then we're going to set the brightness to the maximum brightness on the 7-segment display. Next, we have a function that we're going to be calling in setup. Yes, we're calling it in setup. It's going to say if keys are valid. Now, remember how I asked you at the beginning, you need to type in these keys and you need to make sure that these keys are working. Well, if they're not working, then this is going to return false. That function that validates the keys is the following down here. If keys are valid, this is going to check to see if you actually went through the last one and got the correct keys, because if you didn't, then it's going to return false. After that, nothing will continue on because we're just going to exit the program and nothing will continue going forward. So make sure you have those keys correct. While we're down here at the bottom of our code, let's stop for a moment. Let's look at the other function that we've introduced or created today, and it just says void blink our depth, which quite literally just says, hey, let's display 3 times what our current depth is on and off to the user, and let's display it and blink it however many times that we defined up above. Again, we said 3. If you want to change it up there, you don't have to change it in a million places. Hopping back to setup. If the keys are valid, then we want to show our initial depth. Otherwise, we're going to see a big old nope on our 7-segment display because guess what? Your keys weren't valid. And then we're going to print to the serial monitor saying error invalid keys because you did not get the correct keys. If you don't see this, and it gets past this point, then that means your key should hopefully be valid and there's nothing to worry about. Down below, past this point, we have the following. Interrupts. The new concept for the day, the new fun stuff. Now, assuming you're using pins 2 or 3, we're going to use the digital pin to interrupt clock pin and DT pin, which again, as you can see, is quite literally what we put the rotary encoder on. Pins 2 and 3 is what's required for this to work. So the rotary encoder does not work well unless you use interrupts. There are other ways that this can be implemented, but it's going to work very poorly without using interrupts in your code. I could go into a lot of reasons why that is, but you can just trust me on this. There are a lot of bugs if you don't use an interrupt. There are going to be 2 different interrupts that we're going to be defining. Again, this is in setup. This happens beforehand. It needs 3 things in each one. One is the pin that we're going to be using. It is a digital pin to interrupt. We're going to set depth control clock pin in this case, and then the second one, the DT pin, as the one that's going to be watching throughout the entire code to check to see when it changes. That's the third macro change. If it's a change on here, if anything changes, it's going to then do something. What is it going to do? It's going to call a function. And that function is something we've defined down below called update encoder. So anytime this changes, we're going to update the encoder. Or we're going to call the update encoder function, which simply just does this. Depth control dot service. The service function handles all of the calculations that track turning off the dial and update the counter, which we'll be reading inside of our loop. Since we don't want to reinvent the wheel, let's let the library do it for us. After those are all defined, we can hop down to loop. Now this first if statement says the following. If depth control dot get change. Get change checks the previous value when going through the loop, this time going through the loop, if the value is different. If, let's just say you went from -60 and you went up to -59, and this time, and then by this time of the loop, because the interrupt happened, it's at a different value. That would turn this to true, meaning we're going to go and execute the rest of this code. If there hasn't been any changes, we don't need to execute anything down here below. So you can just ignore it for right now. But everything, for the most part, is all inside of this if statement. So only if something changed do we want to do anything. Int current depth is going to be equal to our initial depth, which is -60 plus depth control dot get count. So what this means is that the very first time we go through the loop, we're going to have a get count of 0 because we didn't turn it at all. Next time we go through the loop, we're going to have a value of 1. So we're going to have -60 plus 1, -60 plus 2, -60 plus 3, etc., etc. And that's going to continue to get us our current depth because, again, we're 60 underwater. So let's just say you think you, being the big old smarty that you are, Mr. Wise Guy, think, hey, you know what? I'm going to go to the left immediately from the beginning, which I don't recommend you do. But let's just say you try it. Well, we have a safeguard for that. We can't go deeper than the -60 because we're already at the ocean floor. So what we're going to do is we're going to say if the current depth is less than the initial depth, meaning we went through right here and we decided, hey, let's try to get down to -61. Ha 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 ha. Mr. Wise Guy. Then we're going to say, yeah, no. And we're going to reset the control to go back to 60. But let's just say you were actually doing this legitimately and not being Mr. Wise Guy. We want to display what the new depth is. And then we want to then just add a very, very short delay here. Now, to prevent stress on our lander, we don't want to rise too rapidly. We want to make sure that we rise at a rate that isn't going to kill us. So in order to do that, we're going to add in a couple of different checks to make sure that we are stopping at the right places. So in this case, we're going to have the static int previous depth, which is going to be the depth that we had from the previous time in our loop. So last time we went in our loop, let's just say we had negative 60, and this time we have negative 59. That's going to make this is going to be obviously negative 60 in comparison to the negative 59. Now, like I said, we have two places we want to be careful at, or we want to kind of stop at a couple different places, just to make sure we're not going up too fast. If we have crossed our first level, then we want to blink our depth to alert our explorer. And if we pass our second depth, which again, alert depth 1 and alert depth 2. Where could those be? Oh, right here at the top. They're constants. If we've passed those two depths of water, then we want to blink those and just make that known. If we've made it all the way back up to 0. Now remember, the surface depth is defined as 0. If our current depth is greater than or equal to the surface depth, meaning we've made it back up to the surface, we want to display done on our 7-segment display as a little congratulatory message for you getting out of the water. And with that, that should be all of the code explanation for day 18. I wish you good luck tomorrow on the travels back up to the ocean surface.
Welcome to the Day 18 wiring example video. It looks like you were successful in decrypting the codes needed to access today's module and are ready to move forward to the next step. At least I hope you were, or this might turn out to be a short session. Today, we'll learn to use a new control device, a rotary encoder like this one. When connected to the Hero, it can provide information about the direction and amount of rotation applied to it. With an angular resolution of 1/10 of a rotation, we'll be using the encoder here to simulate the control of the ascent of our vehicle while using the 4-digit display that we learned about last time to monitor our progress. Now, let's have a look at the connections of the encoder and how we've incorporated it into our system. We see that it has 5 pins, although we'll only be using 4 of those today. Just like the display unit, the 2 bottom pins right here are for ground and plus 5 volts, and they're also connected up here by the traditional black and red wires that we usually use for those functions. You'll notice that we've set up a ground bus and a 5-volt bus over here on our breadboard to be shared by the encoder and by the display, so that we'll only need a single connection to the Hero to provide ground and VCC to both of these devices. So here you can see is our 5-volt connection to the Hero, and this black wire provides the ground down to the ground bus on our breadboard. A quick note in passing here, you can see that we've chosen to use some fairly long wires to provide the connections to both the display and the encoder. And although theoretically we could perhaps choose to plug these components directly into the breadboard, but this would orient those parts at an awkward right angle, rendering them difficult to see and difficult to use. So for the sake of user friendliness, we've opted here to mount them horizontally on my custom work platform and wire them up this way. And so you should feel free to use your own ingenuity to mount these components in a way that's convenient for you. Pause the video at this point if you want to take a minute to study this setup and satisfy yourself that it's equivalent to what's shown in the wiring diagram. Okay, moving along, let's have a look at the upper 2 pins of the encoder. You can see that they are labeled CLK and DT. These two pins send the data to the Hero that allows it to determine the direction and amount of rotation. Consistent with our software sketch, we've connected these two upper wires to pins 2 and 3 respectively. Now, the middle pin on our encoder here is labeled SW for switch, and it's used to detect button presses on the encoder shaft. So if you press on the shaft of the encoder, it's a push button. Now, we're not using that feature in today's project. So, on our circuit, we've left that pin, this purple wire here, unconnected because it's not being used today. Now, as before, the display will be using pins 6 and 5 for its CLK and DIO functions. So, as far as the display is concerned, there's nothing new for us here since day 17. One last note here. I've decided to make a little plastic knob to put on the encoder shaft here to make it just a little bit easier to adjust finely and also to see what we're doing so that we can see how much we rotated it. So I'm going to go ahead and add that knob to the encoder shaft right now so that we'll have that ready for us when we're ready to run the script. So once the sketch is loaded, along with the new libraries that we'll need to support our encoder hardware, the Hero should start looking for interrupts from the encoder and using those interrupts to signal any change in its position, any change from its initial angular position. Then the display will be updated to reflect this change, and this process will continue with you, the human, as actually part of the control loop as you work at achieving your goal of ascending at a particular rate. But now, before we can get on with this task, we need to unlock our system using the secret codes that you should have discovered on day 17. Now, let's have a look over at the IDE and look at the top of today's sketch. And what you'll see highlighted here is that there are 3 constants defined, which should ideally contain our secret keys. But you'll notice that they are currently set to zeros, so we don't expect them to work. And we can go ahead and try and run the sketch this way and see what happens. I'll go ahead and upload the sketch, and we'll see what happens on our display. Okay. So the sketch uploads, and we quickly are told in somewhat untactful terms that we don't have the right code. So what we'll need to do then is we'll need to make sure that we do have the correct codes and enter those in the sketch and save it, and then try and run it again. So I'm going to go ahead and reveal for you another sketch. Now, this sketch contains values that are not 0 for the codes. I want you to note that these are definitely not the correct keys. I've just rigged up this example so that you can see what success will look like when you do enter them correctly. But these are not the right codes. But since I've sort of stacked the deck here, let's go ahead and run the sketch and see if we can practice our task here of gradually raising our vehicle from 60 meters below the surface up to the top, taking a couple of safety pauses along the way that are programmed in to our sketch software. So let's go ahead and upload this sketch. And it looks like we've succeeded here because instead of getting the message that says that we didn't get in, instead we're being told that we're holding at minus 60 meters. So at this point, the hero will be looking for interrupts generated by the encoder, and we should be able to rotate the encoder and change our distance below the surface. So let's go ahead and rotate the encoder counterclockwise, one click, and see what happens. So if I rotate it counterclockwise one click, that raises me up 1 meter. So I'm now at minus 59. I can continue that progress, or if I think I'm going up a little too fast and I need to go back down, I can rotate in the opposite direction and go back to a deeper location. But I think I'm doing okay here. So let's go ahead and continue rising. We can continue our rise, and we're going to be warned when we reach a depth, coming up here soon, of minus 40 meters. So we're 1/3 of the way to the surface now. After we pause here for a moment, we can go ahead. We could go back if we wanted, but we want to continue towards the surface. So here we are at minus 40, and we'll continue until we reach another checkpoint at minus 20 meters. So coming up on 23, 22, 21, and minus 20. All right, so we've successfully reached the 2/3 point. And now we can finally proceed on our final run up to the surface. And again, we could reverse and go backwards if we needed to, but I don't think we need to. It seems like we're going at a good moderate rate. And there's only 10 meters left to go. 9, 8, 7, 6, 5, 4. Okay, we're just about up. 2 meters, 1 meter, and finally 0. And we get the message we were looking for. We're done. So, if you got this to work, congratulations. There is a lot going on here, and the subject of interrupts and all the related issues can be a little bit subtle. So take some time here to enjoy your success and let it all soak in. And once you've mastered this simulation, you'll be ready to move on to day 19, when we will be playing for all the marbles, the actual ascent of our vehicle to the surface. See you then.
Well done, Explorer. Today marked another crucial step in our journey back to the surface. You've successfully installed and set up the rotary encoder, ensuring we have all the tools we need at our disposal. We're now at the threshold of executing our ascent plan. The control systems are primed and ready, waiting oh so patiently for our signal. Tomorrow, we'll be setting our plan in motion, where we'll use our newfound abilities to navigate our vessel back up through the ocean's depths. Remember, our success is built upon the steps we've taken, the knowledge we've gained, and the challenges we've overcome. Get some shut-eye, Explorer. We have an exciting day ahead. See you in the morning.